Problem 2. The radii of curvature of the surfaces of a thin converging meniscus lens are R1 equal to 12 centimeters, R2 equal to 28 centimeters. A. Compute the position and size of the image of an object in the form of an arrow 5 millimeters tall and 45 centimeters to the left of the lens. Is the image real or virtual, erect or inverted, enlarged or reduced? B. A converging mirror of radius 70 centimeters is placed 228 centimeters to the right of the converging lens. Find the position and size of the final image. Is the image real or virtual, erect and inverted, or enlarged or reduced? Draw a ray diagram showing the location of the final image. First thing that we got to do is we got to get the focal length of the lens. So I have R1 at 12, R2 at 28. So a converging lens is thicker in the middle, and therefore we must set up the radii correctly. So if I have the smaller radii on the outside and the larger on the inside, then you could see this is thicker. If I switch these around, you could see that the larger versus the smaller makes it thinner in the middle. Therefore, this is the one we want. So the smaller radii is 12, the larger one is 18 centimeters. Let's calculate the focal length. The left of the lens is the negative, to the right of the lens is positive. Let's calculate the focal length. Focal length is determined by the lens maker equation where R1 is positive 12 centimeters, R2 is positive 28 centimeters. So I'll get 1 over the focal length, gives me this. That I had R squared terms here, which is incorrect. That's correct now. So then I plug in my values and I get a focal length of 35 centimeters. Calculating image S1 prime. So here's my converging lens, f1, positive 35 centimeters. I have an object that's S1, which is 45 centimeters from the lens. So let's draw the ray diagram. I have ray number 1, ray number 2. They converge at this location here, so I can see that the image is going to be inverted, larger, and real since it's on the other side of the lens. Calculating the image distance S1 prime using the thin lens equation. Here's my equation here, so now I got to solve for S1 prime, then get an image distance S1 prime of 157.5 centimeters. Magnification of the first lens is then M1 equal to minus S1 prime over S1, which is minus 3.51 equals to M1. Calculating final image S2 prime. So I now have a converging mirror. It's 228 centimeters away from the lens, and it has a positive focal length of 35 centimeters. So when I look at this thing here, this thing is at 70 at this second focal point here, or 2F point, and this guy is going to be outside of this thing here. So when I draw the ray diagram for this image, it's going to look as follows. So the first ray is ray number 1, so it's parallel, reflects through the focal point, and then I need the one that goes through the middle of the mirror. So I need to set up an equal reflection point. So then I follow this back and then go back to here, and you can see that's where they cross. So the final image looks like it's erect, and it's going to be smaller than the image that produced it. For this object S2, I need S1 prime, which is 157.5 centimeters. I know the distance between these two is 228 centimeters, so therefore the new object is then 128 minus 157.5 centimeters, which gives me 70 centimeters. So now I got all the details here. Calculating the image distance S2 prime using the thin lens equation, I then get a distance of 70 centimeters. Magnification of the converging lens is M2 equals to minus S2 prime over S2, which gives me minus 70 over 70, which gives me a magnification of minus 1, which is equal to M2. Total magnification is capital M total is M1 times M2, so I'm going to get minus 3.5 times minus 1, which gives me a positive 3.51 magnification. So what are the image characteristics? Note that this is to the left of the converging lens, so therefore it has to be a real image. It's erect and it's larger since its magnification is 3.5.